Hello everyone, today we will be presenting our research on the cross-domain transferability of deep autoencoders for IoT anomaly detection. As IoT devices flood our homes and industry, securing this network has become incredibly complex. Today, we will go through how our traditional intrusion systems are falling behind, and why deep learning models struggle when moved to a new environment, and also how we can use dynamic thresholding and explainable AI to bridge that gap. Let's start with the problem. Traditional rule-based security systems are falling behind because they rely on known attack signatures, leaving them blind to new zero-day threats. Unsupervised deep autoencoders are a promising alternative because they learn what normal network behavior looks like and flag anything unusual. However, there is massive catch: domain shift. If we train an NI on traditional corporate IT network and then deploy it into modern IoT environment, its performance completely tanks. The data structure, bursty traffic patterns, and protocols are just too different. This challenge led us to frame three core research questions. Firstly, how does our proposed deep autoencoder perform against standard baseline on legacy data? Second, exactly how much does domain shift ruin zero-shot transferability, and can we fix it without retraining? And last but not least, the third question, how can we use explainable AI, especially SHAP, to understand exactly why the model makes mistakes in new environments? Our methodology relies on comparing two distinct datasets. Our source domain was UNSW NB15, representing stable legacy corporate networks. Our target domain was CICIOT 2023, representing volatile modern IoT traffic. Making sure the model didn't cheat by memorizing IP address or timestamp required us to harmonize both datasets. We stripped them down to 11 shared domain agnostic features, such as time to live, packet size, and protocol flags. We then normalized the database strictly on the source domains. For our anomaly detection model, we designed a symmetrical 848 deep autoencoders. The encoder takes our 11 harmonized features and compresses them down through a 4-neuron latent bottleneck. This forced the network to filter out noise and strictly learn the core pattern of normal traffic. The decoder then tries to reconstruct the original data. During testing, we feed the network traffic into the model and measure the mean square error, or MSE, between the input and the reconstructed output. If a malicious packet enters the system, the model won't know how to reconstruct it, resulting in a high MSE spike, which triggers our anomaly error. We first test our model on its home turf, the source domain. The results were highly positive. Traditional methods like the isolation fortress, and one-class SVM struggle with the high cardinality data, achieving F1 scores of only 0.34 and 0.76 respectively. Our autoencoder, however, captured the complex nonlinear patterns perfectly, achieving a dominant F1 score of around 0.89 with a false positive rate of just 1.02%. The model was ready for deployment. Deploying zero-shot into the CICIOT 2023 target domain, meaning we didn't let the model retrain or adjust its neural weight, was our next step. The result was catastrophic. Using a static anomaly threshold carried over from the legacy data, our false positive rate exploded to 81.33%. Because modern IoT traffic is highly irregular and bursty, the system essentially panicked, flagging almost every piece of normal IoT traffic as a hacker. Realizing we couldn't rely on static threshold in a non-stationary environment, we introduced an unsupervised dynamic threshold calibration mechanism. Instead of a fixed number, the system continuously analyzes a rolling window of 10,000 unlabeled packets in the target domain. It will recalculate the threshold using the median absolute deviation, or MAD, by allowing the decision boundary to adapt automatically to the stream, and we successfully slice the false positive rate down from 81% to just only roughly around 45%, all without us needing a single piece of label target data. Understanding the root cause of this degradation requires looking inside the black box. We apply kernel SHAP and explainable AI framework based on the game theory to map exactly which network features that cause the highest reconstruction error. The summary plot revealed the truth. Features that were highly stable in the legacy domain, like average packet size, TCP, and ICMP protocols, behave wildly different in the IoT domain. The analysis proved that the performance drop wasn't a flaw in our autoencoder instructor, but a fundamental shift in feature behavior across domains. In conclusion, while our 848 the autoencoder vastly outperform traditional baseline locally, static thresholds are entirely inadequate for cross-domain IoT security. Our stream-based MAD thresholding proves that the dynamic adaptation is the right path forward. Though a 45% FPR means it isn't ready fully to autonomous deployment yet, but looking ahead, we plan to explore adaptive window sizes that expand our contract based on traffic volume, as well as few short adaptation to incorporate the tiny amounts of labeled target data for better calibration. That's our presentation today, and thank you.